All right, let's jump straight in today. We're looking at a really interesting paper, cache-to-cache, direct semantic communication between large language models. This one tackles a pretty big issue in multi-agent AI systems.
Yeah, it really does. The core problem, as they frame it, is how inefficient current systems are when multiple LLMs need to collaborate. Think like a coder agent and a writer agent.
Right now they talk using text, right?
Yeah.
Text-to-text or T2T.
Exactly. And TGT forces these models to basically squash their complex internal thoughts, these high-dimensional representations, down into, well, just a string of tokens. It's slow. It can be ambiguous. It's just a bottleneck, a semantic bottleneck.
Okay, so this paper proposes cache-to-cache, C2C. It totally bypasses text.
It does. The idea is to use the LLM's own internal memory, the key value cache, or KV cache, as the communication channel, direct high bandwidth.
Wow, okay. How does that work in practice?
They designed a specific neural network called the cache fuser. And its job is to take the KV cache from one model, the sharer, project it, and sort of inject it directly into the receiver model's cache. It's neural transfer, no text involved.
And the results, what did they find?
Pretty impressive stuff. They saw accuracy boost on average maybe 3.0 to 5.0% better than TTT across their tests. And importantly, a big speed up around 2x faster on average because you skip the whole text generation and parsing step.
So higher accuracy and lower latency, that really suggests KV cache sharing is, well, a much better way for these technical systems to collaborate.
Definitely. It kind of elevates the communication protocol up into the model's own representation space. Okay, so that's the 1-minute overview.
Great summary.
All right.
Now let's dig deeper into that first point, the semantic bottleneck of text. We use text all the time. It feels universal. Why is it such a problem when two advanced LLMs try to use it for technical collaboration?
Well, it's not that text is inherently bad. It's just, think about the bandwidth. An LLM is operating internally with these huge complex states, thousands of dimensions maybe.
Yeah.
And TTT forces it to compress all that richness down into a flat linear sequence of tokens. Model A compresses its thought, sends the text. Model B has to decompress it. You're just bound to lose information, lose nuance in that process.
It's like trying to describe a complex image over a bad phone line. Some details just get lost in translation or compression in this case.
Exactly. And then there's the other big issue, ambiguity. Natural language relies heavily on context, which humans are great at, but for a precise technical task between AIs, ambiguity can really mess things up.
They had a specific example, right, with a coder and a writer.
Yeah, a really good one. The coder LLM generated some HTML and needed the writer LLM to insert content. It sent a text instruction. But the text instruction just wasn't enough. It couldn't convey the structural meaning behind a simple tag, like P, the paragraph tag. The coder understood. It implies a block, a place for content. But the writer, just seeing the text, misinterpreted where to put the content. The crucial structural semantic was lost.
So the intent, this is a container ready for text, didn't survive the T2T process. And you mentioned latency earlier too. That sequential decoding, token by token, for every single message back and forth, that adds up.
Hugely. It makes the whole interaction slow and clunky. So yeah, the paper really poses the question, can these LLMs actually communicate beyond just swapping text messages?
And their answer is yes, by tapping into that internal memory, the KV cache.
Precisely.
So let's talk about that. Section 2 in the paper is all about justifying the KV cache. They didn't just assume it would work. They ran these foundational experiments, oracle experiments, they called them. First, maybe a quick reminder, what exactly is the KV cache again?
Sure. So during inference, especially when generating text, the LLM calculates key, K, and value V vectors. For each token, it processes based on the attention mechanism. The KV cache just stores these computed K and V states.
So it doesn't have to recompute them for tokens it's already seen.
Right, it speeds things up massively. But crucially, it's also this rich, high-dimensional record of the context the model has processed so far. That's what C2C wants to leverage.
Got it. So Oracle Experiment 1, cache enrichment. What were they trying to prove here?
They wanted to know if the quality of the information in the cache mattered. Separate from just how much stuff or how many tokens were the cache you had, does a better cache help, even if it's the same size?
How did they test that? They had a few setups. Direct, few shot.
Yeah, direct was just a short input, let's call it X. Few shot gave it some examples first, then the input EX, so it had a longer context, a bigger cache. But the clever one was the Oracle setup.
What did they do there?
They started like the two-shot setup. They fed the model the long sequence, EX, to let it build up a really rich, high-quality cache. But then, and this is the Oracle part, They basically went in and surgically removed the part of the cache corresponding to the example's E.
Ah, so they ended up with a cache that was the same size as the cache from the short direct input X, but the cache content itself was informed by the richer context, EX, it saw initially.
Exactly. They fixed the cache length but boosted the semantic quality. And bingo, the Oracle setup significantly outperformed the direct setup. Something like 62% accuracy versus 58% with the same cache size.
Okay, so that proves it. Embedding quality is key, not just context length.
Definitely.
Yeah.
But there was another crucial finding here about which parts of the cache matter.
Oh, right, the layer specificity.
Yeah, they found that enriching the cache wasn't uniformly good. If they selectively boosted the cache quality and the layers that were already performing well, accuracy went up. But if they tried to boost the layers that were performing poorly,
Performance actually went down.
it did. Which immediately tells you, if you're going to build a system like C2C, you can't just blindly dump the sharer's cache into the receiver. You need to be smart about it, selective. You need some kind of gating mechanism.
Makes sense. Okay, that leads nicely into Oracle Experiment 2, cache convertibility. The big question here is, if Model A and Model B are different, maybe even different sizes or architectures, can you actually translate the cache from one to the other? Do they even speak the same internal language?
Right. Can you map Model A's internal representation space onto Model B's? To test this, they train a very small network, just a 3-layer MLP.
Tiny.
Yeah, tiny. Its only job was to learn a mapping from the KV cache of a source model, they use Qwen 3.4b, to a target model, a smaller Qwen 3.6b.
And did it work? Could the little MLP translate the cache?
It could. They used TSNE visualizations, which help visualize high-dimensional data, and they showed really clearly that the MLP could take the source cache points and map them successfully into the target model's existing representation space.
Yeah.
It proved that, yes, cache conversion is possible, even between different models.
But there's a subtle point, too, about where in the target space the converted cache landed.
Yes. The converted cache from the sharer only occupied a subset of the receiver's total representation space. It didn't overlap completely.
Which suggests...
It suggests that the models have different strength, different ways of encoding information. The sharer has valuable context, but the receiver also has its own unique understanding. They're complementary.
So fusing them together potentially gives you something better than either one could achieve alone, like combining two experts with different specializations.
Exactly. That's the core value proposition, transferring complementary understanding.
Okay, so those Oracle experiments really lay the groundwork. They show the cache has high-quality information, it needs selective application, and it can be translated between models. Now, let's get into the C2C architecture itself, the cache fuser. How does it actually do this fusion?
The main idea they use is what they call residual integration. It's designed to be non-destructive. It doesn't just overwrite the receiver's cache, it adds to it, enhances it.
And it has specific modules to do this.
Right, 3 main parts shown in their diagram. First is projection and fusion. This takes the sharer's KV cache, runs it through a projection layer to match dimensions, concatenates it, or stacks it with the receiver's own cache, and then passes it through a fusion layer to mix them together.
So just combining the raw materials.
Pretty much. Then comes the dynamic weighting module. This is where it gets smarter. It looks at the actual query the receiver is working on and dynamically adjusts how much influence the sharer's projected cache should have, kind of like turning knobs up or down for different parts of the incoming context.
Okay, so it's input aware. And the third part connects back to that layer specificity finding from Oracle 1.
Exactly, that's the learnable gate. This module learns, on a per-layer basis, whether it's actually beneficial to inject the sharer's fused context into that specific layer of the receiver.
So it can just decide, nope, not helpful for this layer, and shut it off.
Precisely. They use a technique called Gumbel sigmoid annealing to train it, which basically lets it learn a soft maybe during training, but forces it into a hard yes or no during inference for efficiency. It stops noisy or unhelpful context from messing up sensitive layers based on what it learned in training.
Very clever. Okay,
Yeah.
but hooking up two different LLMs like this must bring challenges. They mention alignment issues.
Yeah, 2 main ones. First is token alignment. Different models use different tokenizers. So the same piece of text might get split into tokens differently by the sharer and the receiver. You need to line those up somehow.
How do they handle that?
Their approach is to take the receiver's tokens, decode them back into plain text, and then re-encode that text using the sharer's tokenizer. That gives them correspondence.
What if one receiver token maps to multiple sharer tokens?
Good question. They use a strategy called maximal coverage selection. Essentially, they pick the mapping that keeps the most surface-level string similarity, trying to preserve the meaning as closely as possible across the different tokenizations.
Okay, that makes sense. And the second alignment challenge, layer alignment. How do you decide which layer in the sharer corresponds to which layer in the receiver, especially if they have different numbers of layers?
They tested a few ways, but settled on terminal alignment. This means they start by aligning the very last, deepest layers of both models and then work backwards.
Why from the end?
The thinking is that the deepest layers in a transformer capture the highest level, most abstract semantic concepts. Aligning those core understandings first is probably more important than aligning the earlier layers that deal more with surface features.
Right, align the core meaning first. And a really key practical point, they don't retrain the big LLMs themselves, right?
No, absolutely not. That would be way too expensive. Both the sharer and receiver models are kept completely frozen, their weights unchanged. The only thing they train is that relatively small cache fuser module.
How do they train just the fuser?
Using a standard approach. Next token prediction loss. They basically ask the receiver to predict the next token, but they feed it the fused KV cache, its own cache enhanced by the fuser, using the sharer's cache. So the fuser learns to provide useful context that helps the receiver make better predictions, which is great because it means you can potentially slot this C2C module between existing pre-trained models without having to do costly fine-tuning on the base LLMs themselves. It's much more practical.
Okay, let's talk results. We mentioned the headline figures 3-5% accuracy gain, 2x speedup. How significant is that speedup in a real system?
That 2.0x average speedup is pretty huge for engineers building these systems. Think about a task that requires multiple back and forth between agents. If each step takes half the time, the overall user experience and the computational cost can drop dramatically. You're literally skipping the entire text generation and parsing overhead for every interaction.
And they had that one case where the speedup was way more extreme, the Quinn 3.4b base model.
Oh yeah, that was wild. When they used the Quinn 3.4b base model as the sharer, the standard T2T method just kind of fell apart.
Why?
Because the base model, not being instruction-tuned, often just ignored the request to provide concise context and instead generated loads of irrelevant, super long text. It just wasn't good at the task of explaining its reasoning via text.
But C2C didn't care about that.
Exactly. C2C grabs the internal cache before the model tries and fails to generate helpful text. So it completely bypassed the base model's weakness, and in that specific scenario, they saw speedups up to 14.41x.
That's a fantastic illustration of C2C avoiding the pitfalls of relying on the model's text generation capabilities for context sharing, and instead leveraging its internal representations directly.
Perfectly put. And it's not just for specific cases. They check scaling too. On the long bench V1 benchmark, which tests performance on long documents, C2C consistently beat T2T across all lengths. They tested short, medium, long context up to 8K tokens and beyond.
And what about model size? Does C2C get better if the sharer model is bigger or smarter?
Generally, yes. They found that as the sharer model got bigger and presumably had richer knowledge, the accuracy improvements from C2C tended to increase faster than the improvement seen with T2T. It suggests C2C is better at actually transferring that more complex, valuable context effectively.
Okay, so the gains are real, but how do we know it's really the transfer of complementary knowledge that's driving this and not just, say, the fact that the C2C setup has a few extra parameters in the fuser?
That's where their Ablation study comes in. It's really important for nailing this down. They compared a few setups.
What were they?
They had the standard single model baseline, just the receiver fine-tuned. Then identical, where the sharer and receiver were the same model, so it was C2C communicating with itself, basically. And finally, the main C2C setup with a different heterogeneous sharer.
And the results?
The ranking was clear. Single performed worst, identical self-communication was better, but the full C2C with a different sharer model performed best.
So communicating with yourself using C2C helps a bit, maybe by adding capacity or a different processing path, but the biggest jump comes when you get context from a genuinely different model.
Exactly. It confirms the core gain is from transferring that complementary understanding knowledge the receiver didn't have on its own.
That's compelling, and they even tried to measure this enrichment directly using something called effective rank analysis. What is that, and what did it show?
Right. Effective rank is basically a mathematical way to measure the intrinsic dimensionality or the richness of the information in a data matrix, in this case, the KV cache matrices. A higher rank means more complex, less redundant information.
So if C2C is truly enriching the context, the rank should go up.
That's the hypothesis, and it's exactly what they found. After applying C2C fusion, the average effective rank of both the key cache and the value cache in the receiver model consistently increased.
Do you remember the numbers?
Yeah, for the K cache, it went up from around 388 to 395 on average, and for the V cache from about 532 to 560. It's solid numerical evidence that C2C is successfully injecting new, valuable, non-redundant semantic information into the receiver's context.
Wow, okay. So quantifiable enrichment. The last piece of analysis I found really cool was looking at how those learnable gates behaved. You mentioned they adapt.
Yeah, this is super interesting. It shows that Fuser module isn't just a dumb pipe. It learns different strategies depending on the task it's trained for.
How so?
When they trained the CDC system on a very general data set like OpenHermes, aiming for broad conversational ability, the learnable gates stayed almost fully open, like over 98% activated across the layers.
So for general tasks, it lets almost all the context through.
Right. In that mode, it seems to rely more on the dynamic weights to fine-tune the context flow for each specific query. It keeps all information potentially available and uses the weights for modulation.
But what happened when they trained it on something very specific, like the MMLU benchmark, which tests academic knowledge?
The behavior flipped. The gates became much more sparse. Only about 53% were activated on average.
So for a specialized task, it learned to physically shut off context injection for almost half the layers.
Exactly. It learned that for this narrow task, information from certain sharer layers was consistently not helpful, or maybe even noisy. So it used the gate mechanism itself as the primary filter, selecting only a core subset of layers that reliably provided value for that specific domain.
That's really adaptive. It shows the fuser learns distinct strategies. Broad access for general tasks, aggressive filtering for specialization.
It really highlights the sophistication of the approach.
Okay, wrapping this up, it feels like C2C presents a really strong case. It's positioned as a general, practical, and efficient alternative to just using text when you need LLMs to work together closely. Better performance, lower latency, and now we see proof of actual semantic enrichment.
Absolutely. And the paper points towards some really interesting future directions based on this. One that stood out to me was privacy-aware cloud edge collaboration.
How would that work?
Imagine you have a powerful LLM in the cloud and a smaller one on an edge device, like your phone. Instead of sending potentially sensitive raw text prompts back and forth, the cloud model could compute a relevant KV cache segment, maybe compress it, and send just that curated cache data to the edge model via C2C.
So you boost the capability of the edge device using the cloud model's thoughts without exposing the raw data. That limits bandwidth and privacy concerns.
Exactly. Another area is integrating C2C with other inference acceleration techniques. You could potentially use cache sharing to improve speculative decoding or route processing between different specialized models even more efficiently.
And they also mentioned multimodal integration.
Yeah, extending this beyond just text LLMs.
Yeah.
Imagine fusing the KD caches between, say, a large language model and a vision language model, VLM, or even a robot's vision language action, VLA policy. Direct semantic transfer between modalities.
That opens up a lot of possibilities. Which brings us to a final thought. C2C demonstrates very clearly that deep, effective communication between AI agents can happen without human-readable text, directly at the level of internal representations.
Right. It's more efficient that way for them.
So, thinking ahead, for highly specialized, complex collaborations between multiple AI systems, will we see a future where the primary communication protocols completely bypass text? Will the crucial context being shared between agents become essentially these cache projections that we as the humans overseeing the system might not even be able to directly interpret or monitor in a meaningful way?
That's a fascinating and slightly unsettling thought, isn't it? Efficient for the machines, but perhaps less transparent for us. Something to definitely keep an eye on as these systems evolve.